some elementary induction problems. Okay. The sum of the first n odd integers is n squared. Okay, basic step. 1 equals to 1 squared. Inductive step. Suppose 1 plus 3 plus 5 plus 2n minus 1 equals to n squared. So we assume truth at level n. We want to move on to prove that truth holds at level n plus 1. So what we want to show that the same statement is true at the next level. So 1 plus 3 plus 5 plus 2n minus 1 plus the next odd number after 2n minus 1 will be 2n minus 1 plus 2, which will be 2n plus 1 equals to question mark. It's not over until we do it. The next level for a formula is the same formula in which we replace n with n plus 1. So we have n plus 1 squared. So on the left hand side, the next level in a stack, we just keep taking odd number after odd number after odd number. So the next level is taking the next odd number on top of the current stack. So we got the current stack plus the new piece added to it. For a formula, the next level is obtained by replacing the n with n plus 1. Whatever n appears in the formula, put n plus 1. Okay, so how to prove this and therefore get rid of this question mark? Well, we suppose 1 plus 3 plus 5 all the way through 2n minus 1 is n squared for a reason, so we'll use it later. So by the inductive hypothesis, this will be the inductive hypothesis, what we suppose, this will be n squared by the inductive hypothesis. So this is n squared plus 2n plus 1 equals to n plus 1 squared. Smart. True or not? And obviously it's true because basically we get n squared plus 2n plus 1 equals to n plus 1 squared. A very familiar formula. Hence, the sum of the first n odd positive integers is n squared for every n greater or equal to 1. Okay, exercise 2. 2 to the power n is bigger than or equal to n squared for every n starting at 5. So this will be an inequality which we want to prove by induction. Basic step. To the power 5 bigger than or equal to 5 squared, or 32 bigger than or equal to 25. So we check it. Inductive step. Let's assume, so let's suppose 2 to the power n greater or equal to n squared. Note that n is in whatever it will follow, n is greater or equal to 35. What we want at the next level, so we got formula bigger or equal to formula. So at the next level, the next level will be obtained by replacing n with n plus 1 to the power n plus 1 greater or equal to question mark n plus 1 squared. So we suppose to the power n greater than or equal to n squared, which will be the inductive hypothesis, IH, and we want to prove that the same type of inequality holds true at the next level. To the power n plus 1 level, the next level of to the power n is to the power n plus 1, bigger than or equal to n plus 1 squared, which will be the next level of n squared, is n plus 1 squared. Okay, so how to do it? So how to do it here? Typically in the approach with indeed, to the power n plus 1, we want to connect with the inductive hypothesis. So the best way to connect at this moment is to write to the power n plus 1 is to the power n times 2. It's kind of obvious, but now use the inductive hypothesis. To the power n, we already assume that is bigger than or equal to n squared. So to the power n being bigger than or equal to n squared, we multiply by 2. This will be bigger than or equal to 2n squared. Okay. Remember, we eventually want to show that 2 to the power n plus 1 is bigger than or equal to n plus 1 squared. So we started with 2 to the power n plus 1. So at this moment, we only know that 2 to the power n plus 1 is bigger than 2n squared. Everything will be completed if we manage to show that at its turn, 2n squared is bigger than or equal to, so put a question mark, we don't know yet, but if it would be ideal to show that 2n squared is bigger than n plus 1 squared. Because if you do this, by transitivity, read the beginning and the end, we get 2 to the power n plus 1 equals bigger than or equal to n plus 1 squared. So 2 to the power n plus 1 bigger than or equal to n plus 1 squared. So everything depends on whether we can prove this. Okay, so how to prove that 2n squared bigger than or equal to n plus 1 squared? Let's expand n plus 1 squared, so we get 2n squared is bigger than or equal to question mark, so it's not over until we do it. N squared plus 2n plus 1. Simplify n squared, so we get n squared is bigger than or equal to question mark 2n plus 1, right? So let's try to resurface there. So everything boils down to proving that n squared is bigger than or equal to n plus 1. Let's see. Let me continue here. How to prove that n squared is bigger than or equal to 2n plus 1? Remember, n bigger than or equal to 5. Let's try to divide by the dominant term in left and right. Dominant term being n squared. So this is equivalent. So n squared is bigger than or equal to 2 to the power n plus 1, bigger than or equal to 2n plus 1. So 2n plus 1 is equivalent with 1 is bigger than or equal to 2 over n plus 1 over n squared. But don't forget again, n is at least 5. If n is at least 5, 2 over n, because n is 5 or more, is at most 2 over 5. And 2 over 5 is 0.4. On the other hand, the second term, 1 over n squared, because n is 5 or more, n squared is at least 25. So 1 over something which is at least 25 is at most 1 over 25. So the second term is less than or equal to 0.04. So, indeed, so now the proof is complete. So far it was question mark, but the question mark is settled. Disappears once we notice that 1 is bigger than something which could be at most 0.44. So right hand side, it is at most 0.44. So being at most 0.44 is definitely less than or equal to 1, which completes the proof by induction that 2 to the power n is bigger than or equal to n squared for every n greater than or equal to 5.